Let's talk about power balancing in a circuit. In other words, we want to talk about conservation of power. Okay, so in general, if you look at any electrical circuit, we usually have some power sources and some places where, or some energy sources, and some places where energy is being dissipated, right? So, for example, in the circuits we looked at, we have usually a voltage source, which is acting like a power source, and there's a resistor. So, there is energy creation, right? And there's energy dissipation. Now, uh, amongst all this, there is a electrical system which is basically transporting the energy from the energy source to the energy, sink. Let's say sink. Okay. So now, when we talk about transportation of energy, this energy is being transported in the form of flowing charges, right? And when the energy is created, the charges are going from low potential to high potential. And then when the energy is dissipated, the charges are going from high potential to low potential. So, in general, we know from physics that the total energy is conserved, right? So, what this means is, given any system, the total energy created should be equal to the total energy dissipated, all right? So, in any closed system. So, what this means is, then if there's any system which is just transporting energy, then if you look at the total energy being conserved, the transportation system itself cannot create nor destroy any energy. Okay. So then in our electrical system, what we are saying is net electrical energy produced should be equal to zero, right? So that means, if the total energy created is equal to total energy destroyed, there cannot be any energy created or destroyed within the transportation system. In fact, so we are basically separating all the sources and sink away from the electrical system itself, right? So let's take a look at an example. In the simplest possible circuit we've been looking at, so there is a, let's say there is a battery, and then this could be the standard battery which you can buy and store, and which usually the energy is stored in form of chemical energy, right? And let's say there is a resistor here. Okay, so now when the electrons, or when the charged particles, right, when we are think usually the electrons are moving, but we think of positive charges. Okay, so when the charges are moving from low potential to high potential, they are gaining electrical energy, right? So when they're gaining electrical energy, that means they're, what the battery is doing is it's using some of the stored chemical energy and transferring them into electrical energy, right? By moving the charged particles from low potential to high potential. So if you look at the battery itself, or the power source, there's a chemical energy being dissipated and electrical energy being produced. And similarly, on the resistor, there's heat energy is being produced while electrical energy is being dissipated. Okay, so if the chemical energy being depleted is equal to the heat energy being produced, then the net electrical energy produced should be equal to net electrical energy dissipated. So that's basically the whole balancing of power. It basically comes from. So the first, net electrical energy produced should be equal to zero, right? So then how do we convert that statement into a statement based on power? It's, I mean, so this particular statement which says electric energy should be net electrical energy produced should be zero, that should be true for any time interval. Okay, so let's say I'm observing the system from t to t plus delta t time interval. Then in that interval, let's say delta E of t is the net energy produced. Okay, then that delta E should be zero. That means I can just divide that with delta t and say, okay, this fraction should also be zero. And if I set that delta t to, limit tends to zero, then I get power should be zero. The net power in a circuit should be zero for all times. Okay, and then that's basically what we mean by power is balanced in a circuit. That means the net power generated in the circuit should be equal to zero. All right, so then given a circuit, then we want to make sure that, when you, let's say if you calculate or analyze a circuit and come up with voltage and current drops, then this is a very nice way of verifying if your calculations are correct, right? You want to see, okay, first calculate what is the net power being generated in the circuit. That means, well, how much power is being developed, how much power is being dissipated, and make sure that power developed is equal to power dissipated. If that does not happen, that means there probably is a, you made a mistake in analysis of the circuit. Okay, so let's go through a small reminder of power associated with a component. Right, so this is about how do you actually calculate power in a circuit, net power in a circuit. Okay, so let's say there's a component, it could be anything inside here, and the voltage drop from left to right is V of t. That means the voltage at this point minus the voltage at that point is V of t. Okay, and the current flowing through the component in the direction of the voltage drop. Okay, so it's going through the component, not in the other part of the circuit. It's going through the component, and it's going in the direction of the voltage drop. Okay, if that is the case, then the power associated will be V of t times I of t. Okay, the power P of t, V of is equal to V of t times I of t. That itself could either be positive or negative, right? If it is positive, then power is being dissipated within that component. And if it is negative, power is being developed within that component. Okay, and then we discuss that in more detail in the video on power. Okay, so then given any circuit, what we can do is, for each component, you calculate the power associated with that component, right? And you sum up all the positive powers, that will be the total power dissipated in the circuit. And you sum up all negative powers, that will be the total power developed in the circuit. Okay, and then the sum of all powers should be negative of the sum of all negative powers, in which case the total sum, the net power generated will be 0. Okay, so let's look at an example. All right, so this is problem 1.29 in your textbook. Okay, and these are all the the voltage and currents provided in the question, and the signs of these voltages and the currents are given in this diagram. Okay, so let's focus on, let's say, in the component A here. Let me remove this. Okay, so let's focus on component A here. So VA is, VA and the current are shown here in this circle here. Okay, and VA is positive on the bottom, negative on the top, right? So that's how it is measured. So if you look at IA, right, IA itself is not going in the direction of the voltage drop. It's going in the opposite direction of the voltage drop. So my power will be negative VAIA, right? And that comes out to be negative 918 milliwatts. So let's look at B here. Let me remove the previous circles first. Okay, so if you look at B, the current now, IB, is in the direction of the voltage drop, right? So it's going from positive to negative in terms of VB. So that means my power should be positive VBIB, because IB is in the direction of VB. Okay, and then that turns out to be negative 8 and 10. So you can, I went through the entire calculation again for all the components. I would encourage you guys to, before looking at here, just look at the, signs in this diagram and try to come up with your own answers and then match here. Okay, and then we'll give you some more problems in the homework too. And then I, once I calculated all the powers, I'd look at all the sum of all the positive powers and look at sum of all the negative powers, and sum of positive powers should be equal to negative of the sum of negative powers. Okay, so yeah, we'll stop here.